Our next speaker is Tian. He's going to talk about iterative methods in high-dimensional stats.
Cool. Hi, everyone. Thanks for coming to my talk. So I'm Kevin. I'm a fellow for the GMOS program this semester. I'm also a final year grad student at Stanford. And I'd like to tell you about some recent collaborations of mine that fit broadly under the theme of iterative methods in high-dimensional stats. Okay. So in a few buzzwords, I like to describe my research goal as identifying fundamental algorithmic challenges in modern data science and solving them scalably, reliably, and accurately. So these are very fuzzy terms, and I'd like to be a little bit more concrete what I mean. By scalable, I mean I like to consider algorithms that perform well on large data sets. So namely, with fast runtimes, ideally nearly linear or sublinear, operating under common Oracle model access, and flexible in terms of the models of computation they run on, so namely parallel or streaming settings. Okay, by reliable, I mean I'd like to assume as little as possible of the problem and design frameworks which are flexible, namely they don't like overfit to the particular problem. And this is also captured by things like misspecification robustness. And finally, I care about accurate methods. So namely, I like algorithms which have ideally like very strong optimization performance, strong statistical rates, so namely like the error rate and the sample complexity, things like this. And finally, I like to understand what it means to be optimal in the form of lower bounds. Okay, cool. So this talk is more about the techniques that I commonly encounter in terms of facing these big data computational tasks. So in particular, I draw upon two fields techniques. So the first is what I like to refer to as iterative methods. Namely, how do I manipulate the data efficiently? So this comes in the form of tools from continuous optimization and more classical algorithm design, such as numerical linear algebra, data structures, things like this. On the other hand, in order to obtain truly optimal methods statistically, you have to often understand the structure of the data. So namely, this is high-dimensional statistics, where you draw upon things like geometric properties of the data, concentration phenomena, and so on. And in fact, many problems in modern data science benefit from understanding the toolkits of each of these particular fields. But to obtain sort of the best of all worlds, often you have to have a careful interplay between the techniques of both. So I guess these are sort of like a broad overview of the topics that I'm interested in and have worked on to some extent. So if you like any of these, I'm sure we have things to chat about. But for this talk, I'd like to focus on two in particular, which really capture the interplay between these two sets of techniques. Okay, so the first half will be about log-concave sampling, and the second half will be about robust estimation. Okay, so diving right into it, we're going to consider the problem of composite log-concave sampling, where just as an example, you might try to draw a sample from a multivariate normal distribution subject to box constraints on the parameters. So namely, you can think of these as like parameter ranges for each of your dimensions. Okay. So introducing a little bit more notation, this is the problem of drawing a sample from a density proportional to -f minus g, where f here captures the multivariate normal part, and g is the restriction to a box. Namely, it's 0 inside the box and infinity everywhere else. Okay. So a generalization of this problem is the following setup, where f is some nice function, and g is sufficiently simple, but possibly non-smooth. So here you should think like f is like the multivariate Gaussian. It captures something about your generative model. Like it's like you think your data is being drawn from some Gaussian or like a multi-logit distribution. And g is supposed to capture some sort of prior information about your parameters. So namely, maybe you think it's sparse. You enforce an L1 constraint. Or you think it has certain parameter ranges. This is the box constraint. Okay, cool. So in order to sample from this problem, drawing inspiration from this recently explored connection between optimization and sampling, the first thing someone might hope to do is to draw inspiration from composite optimization. So just to give you a reminder of how these methods typically work, when you're just trying to minimize f, which is well conditioned, you typically just like repeatedly call a minimizer to an approximation of f. And the idea is you build better and better approximations. However, when the function you're trying to optimize is non-smooth, perhaps you don't have access to such a nice approximation, but it suffices to just approximate the well-conditioned part and then exactly call an oracle to minimize g. This is proximal methods. And the key sort of idea is G simplicity is reflected in the existence of a proximal oracle, where you can minimize a quadratic approximation plus all of G. Okay, cool. So in sampling world, one might try to pattern a method off of this, where instead of drawing samples from the negation of x of f plus g, you might try to draw samples from an approximation of f minus g. And the hope is that by calling this oracle repeatedly, you can sample from the original function well. And here, the sort of notion of simplicity you might hope for is the existence of a restricted Gaussian oracle, where you can draw samples from a Gaussian restricted by this function g. Okay, so this problem has actually been reasonably well studied, but perhaps surprisingly, strategies of this form aren't known to yield rates that are stronger than general purpose log-concave samplers. So this is sort of like a notoriously tricky gap to bridge between the optimization and sampling settings. Okay, so to extend upon these ideas, we drew inspiration from these Hamiltonian methods in sampling. And the idea of Hamiltonian methods is typically to introduce this dual velocity variable. And on this expanded space, the dynamics have some nice properties, such as time reversibility and things like that. I won't go into too much detail here. But it turns out that this Hamiltonian approach has really nice implications for composite sampling, in particular by expanding the space to be 2D dimensional instead of D-dimensional, and considering this joint density, which couples the two. You can use the dual variable to control the stability of this overall density. And in particular, to sample from this, you just have to show that the thing is close to the original, which smoothness of f will allow you to do, and then an alternation scheme suffices for the joint density. Okay, so under the hood, what's going on is sort of this novel sampling framework, which generalizes HMC and has implications for all manners of structured densities, including well-conditioned, composite, finite sum, and so on. So I thought this is like a cool exposition of how combining ideas from high-dimensional statistics and iterative methods yields new algorithms. Okay, so switching gears a little bit, I'd like to tell you about a problem in robust estimation I've also worked on called list-decodable mean estimation. So in the typical majority inlier setting for robust statistics, typically the classical setting asks you to perform estimation where you have access to a data set drawn from some nice distribution, namely estimate the mean. In the robust setting, you assume that part of your data set is contaminated and in fact not inliers. So drawn from some adversary gives you some additional data points. Okay, and the goal here is typically either to perform estimation in the presence of outliers or to identify who the outliers are. Okay, and in the high dimensional setting where the data set is supported on, say, RD for D very large, this is a somewhat challenging problem, but recent breakthroughs show you could perform various types of estimation in polynomial time. So the problem I want to talk about today is what's known as the majority outlier model of robust statistics, where here you assume that an alpha equals 1 over k fraction of your data set is drawn from some nice distribution, but here k is like much larger than 2, namely a small minority of your data set is nice. And the remaining fraction of your data set is totally arbitrary and given to you by an adversary. And the question is, what does it even mean to perform estimation in this model? So it turns out that that sort of like the information theoretically right goal is to output a list of hypotheses, one of which is close to the estimate of the parameter that you're trying to estimate. So yeah, it's very straightforward to see that like otherwise it's sort of like not identifiable. Okay. So this model is very flexible and has a lot of applications in various settings you might want to consider, including crowdsourcing, graph inference, and clustering mixture models. I won't go into it too much here, but yeah, these all follow as straightforward corollaries. Okay, so to tackle this problem, the first thing we tried to do was build a new, simpler polynomial time method, which really captures the geometry of mixture models in terms of how it's designed. So previous algorithms for this problem that ran in polynomial time typically had very long analyses and were somewhat non-transparent. So the first goal was to like come up with a very concise algorithm for this problem. So here's the entire algorithm. It solves it nearly optimally in polynomial time. And I won't go into it too much, but for those familiar with the majority inlier setting, lines 7 and 8 are the standard like soft iterative downweighting procedure, which is common to most robust statistics in that model. But sort of everywhere else in the algorithm, we had to design new like termination conditions, a new scoring system, a new like sampling method, which really captures the geometry of mixture models and is inspired by it. Okay. So the second question you might ask is, okay, polynomial time is great, but I tried to promise that I would give fast methods. So can we do better? And it turns out you can reduce this problem to nearly linear time using ideas from fast STP machinery. So this required the development of new STP tools, namely like custom chi-fan regret bounds. And in order to cope with the difficulties that come with these like modifications to the algorithmic framework, we had to sort of like really open up every part of this chi-fan regret analysis and say, okay, maybe not everything won't go quite as smoothly as you wanted, but anytime it does, you have some other reason to terminate the algorithm. So this is sort of like a real like coupling of the high dimensional stats tools and the iterative methods. Okay. And so the first work in this series reduced the runtime of this overall algorithm to a polylogarithmic number of kPCA calls, where k is like the inverse fraction of good guys. And since then, we've been able to open it up a little bit more and improve the whole thing to nearly linear time. Okay, awesome. Yeah, thanks so much for coming to my talk, and hopefully you enjoyed it.
Question for Kevin. All right. So our next speaker is Matani Bezra.